Cage type zeolites such as DDR, Chabasite, Adionite, and Linde type A have structures that consist of cages separated by windows whose apertures are indicated here. Typically, these are of the order of 4 angstrom. Such cage type zeolites with narrow windows are used in a variety of applications involving separations of mixtures of say carbon dioxide methane, carbon dioxide nitrogen, carbon dioxide hydrogen. In my talk today, I discuss a peculiar phenomena that is prevalent in such cage type zeolites, and that relates to the preferential perching of CO2 at the window regions, and the partner molecules on the other hand, such as methane, ethane, nitrogen, and hydrogen, prefer to locate within the cages. Put another way, CO2 prefers the window seat in such cage type zeolites. For background on the topic of my presentation today, I refer you to my papers listed here. I want to emphasize in this presentation the important consequences of preferentially locating CO2 in the window regions. I aim to show that such preferential location of CO2 results in the failure of the ideal adsorbed solution theory for description of mixture adsorption equilibrium. In our paper published in Separation and Purification Technology in 2008, we used configurational bias Monte Carlo simulations for adsorption of a variety of gas molecules: neon, carbon dioxide, nitrogen, argon, krypton, and methane in Chabasite, DDR, Adionite, and Linde type A zeolites. And by sampling about 1 million equilibrated conformations and locations of these gas molecules within these 4 cage type zeolites, we determine the percentage probability of location at the window regions. For all these 4 cage type zeolites, we note that CO2 has the probability of about 30 to 50% of locating at the window regions, whereas molecules such as methane, krypton, argon, nitrogen have probabilities less than about 10% to locate at or near the window regions. The preferential location of CO2 at the window regions results in segregation of gas molecules that have important consequences for mixture adsorption. Another way to quantify the segregation effects for mixture adsorption is to determine the radial distribution functions that consists of sampling, say, 1 million equilibrated samples, and to determine the distances of various pairs of molecules. I show here the results for mixtures of CO2 and propane in LTA4A zeolites. LTA4A is a cation exchange zeolites with sodium cations as extra framework cations. These are indicated by blue. The radial distribution functions are shown here. The red line is for CO2-CO2 pairs. The CO2 propane pairs are indicated by the black lines. The blue line indicates the distances between CO2 and the extra framework cations. We note that the location of CO2 is very close to the location of the extra framework cations. This is demonstrated by the fact that the peaks in the blue line and the red line occur at approximately the same distance of separation. So the distance of separation between pairs of CO2 molecule is approximately the same as the distance of separation between CO2 and the extra framework cations. The propane molecules prefer to locate within the cages. This is also demonstrated by the RDF, shown by the black lines, where the peak occurs at a intermolecular distance of about 6.4 angstrom. So CO2 propane pairs are further apart than CO2-CO2 pairs and propane-propane pairs, that is indicated in the blue line. Another way to demonstrate the preferential location at the window regions is to see the various peaks in the CO2-CO2 pair distances. There's a peak at 8.68 angstrom. Why is that? The distance 8.68 corresponds to the distance between that window location and that window location. So the fact that another peak appears here is a further indication that the window regions are preferred locations for CO2. At this distance of 8.68, there is no maximum in the distance between pairs of propane molecules, which are indicated in green. So we can conclude that the preferential location of CO2 at the window regions leads to segregation of gas adsorbates within the pore landscape. Due to the segregation in the location of gas molecules within cage type zeolites such as DDR, Chabazite, Aragonite, and LTA, we have important consequences for the validity of the ideal adsorbed solution theory. The ideal adsorbed solution theory mandates a uniform distribution of gas adsorbates. And if segregation occurs, then the IAST fails to provide a quantitative description of mixture adsorption equilibrium. To demonstrate this, we conducted configurational bias Monte Carlo simulations for adsorption of CO2 methane mixtures in Chabazite zeolite. Two types of simulations were conducted, one for 1585 mixtures, and the other one for 5050 mixtures, indicated respectively by the blue triangles and the inverted pink triangles. The adsorption selectivity is plotted as a function of the surface potential that is a proxy for the pore occupancy, and a value of 0 surface potential indicates vanishingly small pore occupancies, and a high value of the surface potential indicates pore saturation conditions. The dashed lines are the IAST estimates of the adsorption selectivity, and we note that the CBMC simulation data lie consistently below the IAST estimates. This is because the segregated nature of mixture adsorption results in reduced competition between CO2 and methane. Put another way, methane suffers less competition with the more strongly adsorbed CO2 than would have been the case if the guest adsorbates were uniformly distributed. So the CBMC simulation data for the adsorption selectivity are lower than the IAST estimates. If we calculate the activity coefficients in the adsorb phase, we note that the activity coefficient for methane reduces to values below unity, indicating that methane is subject to strong non-ideality effects. For details, I refer you to my publications. For CO2 methane mixture adsorption in DDR zeolite, we conducted configurational bias Monte Carlo simulations for 2080 mixtures indicated by the blue triangles and 50-50 mixtures inverted pink triangles. And for both these mixtures, we see that the CBMC simulation data for the adsorption selectivity of CO2 with respect to methane is significantly lower than the estimates of the ideal adsorbed solution theory. This lowering in the adsorption selectivity is because of reduction in competition between CO2 and methane. Methane suffers less competition from the most strongly adsorbed CO2, and therefore the adsorption selectivity is lower than is anticipated by the ideal adsorbed solution theory. The activity coefficient for methane reduces to values significantly below unity, with increasing values of the surface potential that serves as a proxy for the pore occupancy. A value of 0 for the surface potential implies pore occupancy that is vanishingly small. A high value of the surface potential indicates pore occupancies that approach saturation conditions. To quantify thermodynamic non-ideality effects for CO2 propane mixture adsorption in LTA4A zeolite, 3 different molecular simulation campaigns were undertaken. In the first campaign, the total fugacity of the mixture was maintained at 1 megapascals and a temperature of 300 Kelvin, and the mole fraction of CO2 in the bulk fluid phase mixture was varied from 0 to unity. And the molecular simulation data for the adsorption selectivity of CO2 with respect to propane is plotted as a function of mole fraction of CO2 in the bulk gas phase mixture. We note that there is a selectivity reversal that is experienced for mixture adsorption, and the composition at which the selectivity of CO2 with respect to propane is unity is the azeotropic composition, and has a value of approximately 0.1. The ideal adsorbed solution theory anticipates no dependence of the adsorption selectivity on the mixture composition, and this IST prediction is indicated by the dashed lines, whereas the molecular simulations indicate the occurrence of selectivity reversals, a sure sign of strong thermodynamic non-idealities. Two further molecular simulation campaigns were carried out for 1090 mixtures of CO2 and propane. The total fugacity was increased from very low values, say 1 Pascal, to about 10 to the 7 Pascals, and the CO2 propane adsorption selectivity determined from the CBMC simulations. CBMC stands for configurational bias Monte Carlo simulation, is plotted as a function of the surface potential. The surface potential is a proxy for the spreading pressure pi, and the spreading surface potential is pi times the specific surface area per kilogram of framework divided by R, the gas constant, times the absolute temperature T. The surface potential is calculated from this expression, where P sub 1 superscript 0 and P sub 2 superscript 0 are the sorption pressures, and the integrals are evaluated such that the surface potential or the spreading pressure for mixture adsorption equals the spreading pressure for component 1 and equals the spreading pressure for component 2. If the mixture were to behave ideally, the adsorption selectivity of CO2 with respect to propane would show a unique dependence on the surface potential that is a proxy for the spreading pressure. And this IEST prediction is indicated by the dashed line. In reality, we have strong deviations from the estimates of the IAST. Indeed, for 1090 mixtures, we have selectivity reversals at this surface potential value of, say, 28 moles per kilogram. This is the CBMC simulation for an 80-20 mixture of CO2 propane. In this case, no selectivity reversal is observed for the range of surface potentials that are considered. So strong deviations from the behavior anticipated by the IAST. And to quantify the deviations from the IAST, we have to introduce activity coefficients in the expression that relates the partial fugacities to the adsorption pressures P sub I superscript 0, and Xi is the mole fraction of component I in the adsorbed phase mixture. The activity coefficients need to be quantified and modeled in order to be able to quantify the variation of the adsorption selectivity with either mixture composition and or the surface potential phi. For the three sets of GCMC simulations shown in the previous slide, I plot here the activity coefficients for CO2 and propane as a function of either the mole fraction of CO2 in the adsorbed phase mixture or the surface potential. For the campaign in which the total bulk fugacity is maintained at 1 megapascal, we see the activity coefficients have the limiting behavior that as the mole fraction of the adsorbed component I approaches unity, the activity coefficient of that component should also approach unity. For the other two CBMC campaigns, for a 10-90 mixture and 80-20 mixture, we have another requirement for the activity coefficients, and that is that as the surface potential approaches 0, the activity coefficient of both gas molecules should approach unity. This is because the surface potential also serves as a proxy for the pore occupancy. So as the pore occupancy approaches 0, then the gas molecules are far apart and there are no thermodynamic non-ideality effects. So we should have the limiting behavior that as phi tends to 0, the activity coefficient of that component of each component in the mixture should tend to unity. So if we say adopt a Wilson model for quantification of the activities of components 1 and 2, then we should introduce a correction factor 1 minus exponential minus a constant c times phi, and this is a representation of the pore occupancy. And as this quantity approaches 0, ln gamma 1 will approach 0. In other words, gamma 1 should approach unity. Similarly, ln gamma 2 should be proportional to 1 minus exponential minus a constant c times the surface potential phi. So as phi tends to 0, ln gamma 2 tends to 0, and gamma 2 tends to unity. The three constants, lambda 12, lambda 21, and C, can be determined from the three sets of CBMC simulations by applying a regression analysis. And with the choice of these parameters, the molecular simulation data for the three campaigns may be reproduced in a quantitatively correct manner as shown in these figures.